Alrighty, today we're going to be talking about 4.4. Hold on. Yeah. Okay, so again, today we're going to be working on 4.4 other common factors and some technical issues. So, other common functions. The one we're going to basically, our parent function will be our power function. And it is basically written as some coefficient times x to some power r. You can have odd positive integers. So you could have like y equals x, which is just a linear function. You can have y equals x cubed, which is a cubic function. And then as you keep getting larger and larger, it keeps resembling the cubic function. The only difference is this gets a little closer to the y-axis, and this gets a little more narrow as you go. And that might be a little more extreme there, but that's the process of what an odd positive integer would do for an exponent. All right. Others you might see are even positive exponents. So even positive exponents. And you will have stuff like f of x equals x squared, which is our quadratics that we've been dealing with. And then we can have f of x equals x to the fourth. And what it does, it resembles the quadratic. It just gets a little bit more closer to that y-axis and flattens out a little bit more here. Let me do that a little bit better. Flattens out right there, and then comes up a lot quicker. And it kind of progressively gets more narrow and more flatter the larger my exponent gets in the positive direction. Then we have odd negative exponents. So the most famous one is x equals to the power of negative x raised to the negative 1, which is 1 over x. These are what we call our rational functions, basically functions that have fractions. And this is what the parent function would look like. Now, as we get larger and larger, what we will see is these are called branches, and the branches will get closer and closer to the origin. So it'll look more like this. And so as it gets larger and larger, these gets closer and closer to the origin, and these get closer to the x and y axis. Because it's getting, technically, it's getting bigger faster or slower in a sense in some directions. All right, so that's kind of what an odd negative exponent would look like. Then we have even negative exponents. And those are going to be in the form of like f of x equals x to the negative 2, which is the same thing as 1 over x squared. So they look, again, they have branches, but then they will both be on the same side. So you have them like this. And then as you get bigger and bigger, it just gets closer and closer to the origin. So it'll look more like this right here. And this right here. So you can see that they're getting closer and closer to the origin. So that pattern just keeps on going. All right. And then we'll go with odd denominators. So that would be like f of x equals 1 over, or sorry, x raised to the 1 over 3. 1 over 1 would just be a linear function. But let's say we have odd denominators starting with 1/3. You'll actually see it'll kind of make a cubic function. but sideways. And so if I do another one, so like x to the 1/5, it makes the same one, it just gets a little bit more narrow. And as it progressively gets technically smaller, the graph itself will get closer and closer to the axis. And then we have even denominators. I think the books are calling these roots. It's probably more accurate there because they are radicals. So I can have something like f of x equals x to the 1/2, which is the same thing as the square root of x. If I go back real quick, this is the same thing as the cube root of x, and then the 5th root of x, and so on and so on. So a square root or a radical function just does something like this. And so then if I go to x to the 1/4, the same thing as the 4th root of x, basically does the same thing. In a sense, though, this kind of jumps up a little faster, a little bit sooner, and then kind of plateaus a lot sooner as well. And then that pattern just keeps on going. All right, then we have what we call absolute value functions. And those are going to be the functions of the things with the absolute bars, and they resemble a V. This is actually your first type of piecewise function. So this would be the same thing as I would graph regular x as long as x is greater than or equal to 0. Or I would graph negative x, which is this direction, if x was less than 0. So this is actually your first piecewise function that you have. Alrighty. Another type of piecewise function is what we call the greatest integer function. And that's in the form of, it looks like absolute, but it's like a double bracket here. So that's what it kind of looks like there. And basically what happens is the graph. So if I say, hey, what is f of x equals the step function of 2.5? Or let's make it just, yeah, 2.5 is fine. So what is 2.5 between? So you have to ask yourself, hold on, make sure I get this right. Yeah. So you ask yourself, what is it, but the two functions it's between? So like, for example, like the book uses 4.3, so I'm going to use that one. It's between the integers of 4 and 5. And the greatest integer kind of gets a little misconceived because really 4.3 is between 4 and 5, but you actually go down to the smallest integer. So it's called the greatest integer function, but in reality, when you're evaluating the function, you look at, all right, what is this integer between? So in this case, 4 and 5, and then you go towards the smaller integer. So the other example here as well was negative 2.9. It's between -3 and -2, and -3 is the smaller integer. All right, so even though it's called the greatest integer, you look at what it's between and you go to the smaller one. And so when you graph that, you get functions that look like this. And it's what we call also a step function. And you can go the other way as well. And so you get something like this. So this is your, I would say, your next most famous piecewise function. And again, both of these are called Do a different color so you can see it. This is a piecewise function. And what makes it called a piecewise function? It's pieces of other functions. So these are technically constant little functions all the way down or all the way up, depending on how you look at it. All right, so this homework is actually relatively straightforward, and you could probably use your calculator to answer most of these questions. But as your professor, I do want to kind of explain what each function is, just in case you get a professor that doesn't allow calculators. So, like for instance, we're going to be on page 278, and I want to look at example 6. It says q of x is equal to negative cube root of x. And you're asked to sketch the graph of the following functions and then pay particular attention to intercepts, if any, and locate these accurately. So basically what you do is again, you could type this straight into the calculator. But what I'm going to do is I'm going to identify what this parent function is. And I see that this is a cube root of x, which could technically also be written as this as well. So when I graphically look at this, I know originally it looks like this function here. So x cubed, so x to the 1/3 from our notes, look like this. And a negative is just going to flip it across the x-axis. And we'll get more into that at the end of this section. So when I graph it, I should roughly get something like this. And I think on the test, or the test, on the homework, you're just identifying which graph it is. You don't actually have to graph it. You could use your calculator, yes, but you don't necessarily have to. All right, so that's basically all we do. So let's see. So I'll do another one. I'll put on the same page here. So we'll do number 8. This one is k of x equal to 1 over x cubed, which can be written as x to the negative third. And what I know from this one, from my notes, is that this is an odd denominator or odd, or a negative odd integer. So I know that this is going to be the branches, and they go on opposite sides. So then I know this is what my function looks like, right? And again, that's really all you're having to do here. And I think on your homework, you're just picking the right answer choice. So let's look at number 9. So number 9 is g of x equal to the square root of x over 2. So I can see that this originally comes from the square root of x family, which again can be written as x to the 1/2. So that's going to be a function that looks like this. So if it's a half of that, think of it as if you plug in some values. So I plug in 4, I typically got 2, but I'm halving that so I get 1. So that's going to tell me it's going to take a lot longer to get up there. So I might have a new function that looks like this, rather than just shooting up to the top. It's going to take a little bit longer because if I go to 4, I'm only going to have 1 as my result, right? So could have a function that looks something like this, just knowing from what I know from my parent function. Again, you can sketch it as well. Let's look at number 12. So number 12 is p of x equals negative 1x squared. This can be written as negative 1x to the negative 2. So that tells me the parent function of x to the negative 2. So a negative even one had the branches that were on the same side. And because it's a negative, I know that's going to flip across the x-axis. So this function will probably look something like this, right? In the ballpark range. All righty. Let's do a few more of these. So let's look at number 14. 14 is k of x equals x cubed over 9. And again, this comes from that parent function of x cubed, which I know looks like this. And so when I'm looking at this, I'm going, man, if it's divided by 9, it's probably not going to shoot up as fast. So my function might be a little bit more spread out now, maybe. It's going to divide it by 9, so I'm not going to be able to shoot down as fast as I was. So I think in the ballpark area, this is what my function would look like. On number 19, we have something that looks like cubed root of x. Oh man, let's rewrite that. Cube root of x over 3. Again, that comes from the parent function of the cube root of x, which is x to the 1/3. So I know that looks something like this. And again, if I'm dividing it by 3, it's probably not going to shoot up as fast. So I might have a little bit more spread out type of function. Right? Let's look at number 20. So number 20 is s of x equals the absolute value of x over 3. So again, this comes from that parent function we just discussed with the absolute value function, which we know looks like this. And because it's divided by 3, it's probably not going to shoot up as fast. It's probably going to be a little bit more open. Let's look at number 21. So this is t of x equals x to the 6th divided by 4. Again, that comes from that parent function of x to the 6th, which is going to be pretty narrow and then pretty flat. So it's going to look something like this. But when I divide it by 4, maybe it just does it a little bit less. So maybe a little bit more wider, maybe a little less flat, and a little bit more wider this way. Could potentially be something I'm looking for. All right, so looking at number 25, this is a piecewise function, so we'll kind of slow this roll just a little bit. So 3 minus x if x is less than -2, and x to the 1/3 if x is greater than or equal to -2. So I look at this graph here. I need to graph these piecewise functions. So you're going to start off with what I like to call the breaking number. So I'm going to go to -2 in my function. So if I go to -2, I get 3 minus -2, which is a positive, and that would give me 5. So that means at -2, I go to +5. I'm going to put an open circle. The reason I'm going to put an open circle because there's not a line. This point will not be included in my set. Now, after this point, I just need to kind of look at my information. This is a linear function, and we know a linear has a y-intercept of 3, right? But this is everything less, so I'm not going to make it to that y-intercept. And then this has a slope of -1/1, right? This has a 1/1 situation. Now, typically, I always say go down 1, right 1, but because I can't do anything on the right side because it's everything that's less, I need to do the complete opposite. So then I'll go up 1/1. And at that point, I'll put a solid dot because -3 would be in the set of this function. So if I put -3 is less than -2, this is the function I would choose. So then when I graph it, this is what my function will look like right there. All right, so then I now have this first half. Then at x equals cube, what I like to do first is again plug in that value. So -2, the cube root of -2. Ooh. Oh, it's going to be 1 point something. Might want to pull up a calculator for this one. Might need to switch to a scientific. There we go. So we'll say 2. We'll make it negative. I'll raise it to the 1/3. Oh, never mind. I can't do that. Hold on. Let's see. So again, 2 negative. Man, I'm not seeing one. If I could do, well, I'll tell you what. We'll get close. We'll just say 0.3, repeating a bunch. Invalid input. Interesting. All right, let's try this. 2 negative. We will raise this to parentheses 1 divided by 3 and enter. And there you go. So you get -1.2. I knew there'd be a way. All right, so we get -2 and then -1.2 would be roughly, I don't know, probably about right here. All right, and this will get a solid dot because this one does have an open circle. I know a cubic function is going to look like this right here. And because I don't graph anything on the left, I graph it on the right. I'm going to kind of resemble that. So I'm going to kind of come here, and then I'm going to kind of plateau. Now, if you want to get more specific, you can choose other numbers. I know I'll have a point at 0. I know if I went to 1, I would have 1. And then 2, 3, 4, 5, 6, 7, 8, I know would be 2. So maybe I went too far up, but this would roughly be 2. And I can get more accurate with it if I needed to. Alrighty, so that would be a piecewise function. It's literally pieces of a function, and you graph it corresponding to what the x tells you you can. All right. Let's see. Let's do one more, and I think you have as many examples as you would need. All right, so let's look at 44. 44 is f of x is equal to negative 4x minus 12 if x is less than or equal to negative 3, and then 5/10 x squared if x is greater than negative 3. So again, if this is a multiple choice question, I'm looking for a piecewise function. So on this one, I think it's definitely going to have to be A through F is mismatched. But I see I have a linear and a quadratic. So I'm kind of looking at that. And the only one that really has a linear and quadratic would be B. So without actually having to graph it, just with my default of what information I know, linear and quadratic, I'm good to go. But just in case you have to do it by hand, ever, I'm going to start with that negative 3. And when I plug it in, that would give me negative 4 times negative 3 minus 12. So that would be negative 12 minus 12, which is negative 24. And so at negative 3, 1, 2, 3, I'd go 1, 2, negative 3. Oh, gosh. Sorry about that. But so this isn't going to map out right. So negative 3 times negative 4 is positive 12 minus 12 will give me 0. That's a lot easier to do. So at negative 3, I would have a spot at 0, and that's as far as I can go from the right. So then from there, I know my slope is negative 4 over 1. So instead of going down 4, right 1, I'll go up 4 over 1. So here's my new point. And then this will be what my linear function would look like. Then I'd graph my quadratic. Again, starting at that negative 3. Well, negative 3 squared is 9. Ooh. And that right there would give me 45 over 10, which is about 4.5. So I would say, all right, so at negative 3, I need to go to 4.5. So 1, 2, 3, 4, 5. And I would put a open circle, again, because it does not have the line over it. And then I know that the quadratic does something like this. So I'm just going to kind of finish it off as such. And again, you can pick some good points. You can choose 0. You can choose other numbers if you would like, and then it makes it a little bit cleaner. All right, but that's on a test that I would give. That's all I would be kind of looking for. All right, so that's pretty much it with that one. If you have any questions, just continue to email me. And then I'll see you in the next video. Bye for now.